NASA's explorers today have a lot in common with explorers from the 16th and 17th centuries who left Europe seeking a new world. Both set off in small crafts with just enough space for themselves and a few necessary tools. And the need to find life-sustaining resources in their respective new worlds was and is crucial. But the new world of space is a little different than the new world that became America. Question is how to turn this into this.
We'll dig up some answers next on Real World.
When it comes to space exploration, we humans have always taken the supplies we need to survive. Water, oxygen. We had to bring it to the moon and to space stations we've occupied. This has worked because we haven't strayed too far for too long. But now, NASA is returning to the moon, and this time to stay. So finding and using lunar resources is imperative. NASA calls this in situ resource utilization, ISRU for short. And it's a big part of NASA's plans for establishing human outposts on the moon and eventually Mars. But looking at the surface of the moon, it doesn't really look like there's much to work with. No plants, no animals, no obvious water, just a lot of dust and rocks. But it turns out, that's the key. In the lunar soil or regolith, there are enough chemical elements to make lots of the resources a colony like this would need. But how do we take moon dirt and get oxygen out of it? Well, recently on Mauna Kea volcano on the Big Island of Hawaii, ISRU scientists and engineers took a big step towards solving that problem. There, they tested 2 reactors that can convert the seemingly sterile gray dirt into usable oxygen. Excavating rovers dig up the regolith and deliver it to the reactors. That's when things really start to heat up.
We get the material to the reactor and then we do the chemical reaction and store the oxygen.
Tom Simon is the ISRU Project Office Chief Engineer.
In terms of the chemical processing plant, heat passes over the heated regolith. That's when the reduction takes place. And from that point on, it's mostly cleaning up the water, electrolyzing the water, and then cleaning up the product oxygen.
And surprisingly, it doesn't take a whole lot of digging to provide a pretty healthy amount of very valuable substances.
What we're shooting for is about 1% of the mass of the soil.
Larry Clark is the ISRU Program Manager for Lockheed Martin, one of NASA's partners in this project.
So in this case, we're taking about a 12-kilogram load to make about 120 grams of water. Depending on where we get the soil on the moon, we could get up to 4 times that amount. Conservatively speaking, we've been shooting for 1% reduction, and that's really our bare minimum we've seen with all of our samples so far.
One of the key strategies of ISRU is to develop machines, rovers and reactors that can work autonomously without much help from humans.
So while the machines are busy providing resources, the astronauts will be free to do what astronauts are supposed to do: explore and make discoveries.
On the moon, we would set up a depot, whether it's the fuel cells coming to get oxygen, whether it's the crew coming to get water and oxygen, whether it's the propulsion community coming to get oxygen for propulsion. We would store it in our depot and they would come and get it periodically. For this particular setup, we have a cryogenic oxygen tank here. That tank stores about 8 hours worth of oxygen that we would make. So imagine if we did that 6,000 hours a year, how much oxygen that would be.
We can drink the water, we can breathe the oxygen we make, and we can use it to fuel cell vehicles. Eventually we can get up to a production rate where we can power the ascent vehicle, we could power launchers. Perhaps we could even power hoppers that would take you from place to place on the moon. So there's lots of different things we could do.
NASA sent 2 prototype reactors to test 2 different systems. One of the systems, called Pilot, is designed to sit on top of a robotic lander, meaning it could be launched before sending a crew to the moon, touch down on the lunar surface, and begin to produce oxygen without the need of a human being. The other prototype system, known as Roxygen, is a larger scale system that might require astronauts to set it up. Both reactors worked well in Hawaii, making researchers optimistic that this approach will be successful on the moon. Scientists and engineers are going over the data from the Hawaii test now, trying to optimize the design to create the best system.
More testing and revisions lie ahead.
So, like the adventures of old, a new generation of pioneers will soon leave the familiar surroundings of Earth. And today, the scientists and engineers involved in the ISRU program are hard at work inventing the tools that these explorers will use as they venture out to establish the first human outposts on other worlds.